25 to 3, I got the first messages saying that the students didn't wear the instructions. So at that point, I started worrying, and when more and more came in, I basically then had to go to a different way of distributing the announcement. I basically had to harvest all the email addresses and then send the announcement directly from my Gmail account, which of course delayed things. And so there was nothing I could do. At least I did manage to send out things, although 15 minutes late. What can I say? We're dependent on technology, and if the technology fails, then there is not a whole lot I can do. I have still not gotten any explanation why the UH server didn't operate, but I guess it has now been put back into service because you are logged on, and it was sent out using the UH server again. Although this time, of course, I was prepared to immediately send things from my Gmail account, but this time it wasn't necessary. Just perfect timing, just for the exam. Sorry about that, and we'll try to make sure that we'll do whatever we can to let you recover from that. Now, the acknowledgement that was supposed to be sent out from the submission site was also tied to the UH email server. So the reason why you didn't get any responses was because it didn't work. So I think we got everything that was submitted, except you didn't get any acknowledgement. And so we will grade the exams fairly quickly and post the grades on Blackboard, at which point you can determine whether we actually got what you sent in. And as I had indicated, if we didn't get it for whatever reason, and I'm not really even interested in finding out what the reasons were, then just send us the thing again. Presumably, if you saved it, it should have a timestamp that was Monday timestamp. So sorry about that, but
is there any possibility of using Blackboard or perhaps a Teams in the future?
One of those problems that you run into when you have a large course. If I had 10 students, I could contact each of them individually, but with 240, it doesn't work that way. Any questions, comments, observations?
Yeah, so given that this happened, is there any possibility of considering using Teams or Blackboard for the future tests?
Test.
Do you hear me? Or do we have another failure?
Can you hear me?
Oh, come on. This is getting ridiculous.
I can hear you.
I
but
can
I
hear
can't.
you too.
I'm not sure the professor can hear us.
Right. I was waiting for him to say any other questions.
Yeah, I think.
Yeah, so he can't hear.
Can
But
you hear me?
That's a good question. We should probably ask him on the Blackboard part. I think it'd be easier.
Can anybody hear
to
me?
implement.
Yes,
I can. So we can hear Professor, but I don't think
I can't hear any of you. All right, let's try again. Sorry, yes, now I can hear you. What? Yes, go ahead.
So given that this failure occurred, do you think there's a possibility of perhaps using Teams or Blackboard for disseminating the future and submitting the future tests?
I'll have to look into that. I'm not using Teams. I don't like Teams. Teams has screwed me up many times, so I'm not using Teams. That's not an option. We will have to look into Blackboard, but if something fails, then I'm sure Blackboard would use the UH server as well, and you wouldn't have gotten any acknowledgements from Blackboard either. This was a fundamental failure of a basic system that is completely unconscionable. It was the most trivial kind of thing, the email server of the University of Houston. That's what failed. That was the only problem, only. And if I can't do anything about that. I was in contact with the IT staff in the department, and they couldn't do anything because it was UH. So it's not a question of the modality. If all of these systems ultimately depend on this type of fundamental basic foundation, and if that fails, then there's nothing that works. I mean, we're actually lucky that I managed to harvest all the email addresses and send things from my Gmail account. If I were dependent on the university, that wouldn't have happened at all. So I don't know. I would hope that this is never going to happen again, but then of course, who am I? Any other questions or comments?
Yeah, I have a question.
Sure.
So since I sent my exam through the email, so but didn't get a response, what should I do in my case, like right now?
Just wait. As I said, I sent out an email. Did you get that, saying that you should save what you submitted? And if it turns out that we didn't get it, and I'm told that the system actually, that our system worked quite well. It didn't manage to give you acknowledgements because that depended on the UH email server. But the system actually did receive, I think, everything that was sent in. So we will post the grades on Blackboard, and then you will see whether we got your submission or not. And that point, we will have to figure out what we can do if we didn't get it. But at this point, I am told that virtually everything that was sent in was received, even though no acknowledgement was sent out. So just give us another week or two. Okay?
Okay.
Sorry about that. There's not a whole lot I can do because this is totally out of my control. I mean, I have attempted to keep things as simple as possible. You all know the KISS principle, but of course I do have to rely on certain kinds of things, and I have never had experiences with a failure of the UH email server. So this is now the third semester that I'm using it, and first time, but there's of course always a first time for everything. Anyway, any other questions?
Yes, Professor.
Sure.
So, you asked us to submit through a zip file, right? But my Gmail wasn't accepting the zip file when I tried to attach it. So I sent it through PDF, and then I sent another mail through the UH Outlook mail.
I'm sure that is fine.
Okay, so
we've gotten PDFs in the past, so I don't think that they rewrote the submission system, so it will accept PDFs.
So there shouldn't be any problem instead.
There should not, and you will find out once we post the grades.
All right, thank you.
Okay?
Mhm.
Will we have an opportunity to review our actual like tests and how we missed points, and that way we can learn from our mistakes?
Yes, at some point, once we have graded things, that will give us 2 weeks, and then we'll should have some ability to do that.
Awesome.
Okay?
Thanks.
Any other questions?
Sir,
Yes.
I'm complaining or anything like that, but I could open the website which had the exam file. It was like 15 or 20 minutes after 2 o'clock. I'm sorry, 2:30. So, and I had another exam right at 4 o'clock. So I didn't have enough time and it was so stressful. I think that was because the website was, so many people they were using that website. So I think that caused the problem.
I have no way of. Did anybody else have the problem?
Yeah, I agree.
Yeah, I did as well.
Yes, it was checking to refresh the site for sure.
The problem was that I got started late, and then I didn't check my email to submit it. 15 minutes, the additional 50 minutes to complete the exam. So really, I lost almost 30 minutes that I could have been working on the exam.
But
Yeah,
we gave you an
Professor.
extension of 20 minutes.
I didn't get the instructions until the next day.
Exactly, Professor. We all got the instruction like today, I think. And also, Professor, I am in a different time zone. So my timestamp, in case the email doesn't reach, I'm not entirely sure what to make of it.
If we will contact you if there's a problem.
Yeah.
Professor, I think I have a suggestion, and it's just I feel like last year, whenever we took algorithms, you actually gave us a 4-hour time window in the exams. That being said, like
I don't think I did. I
yes,
never gave you a 4-hour time window last semester.
yes. Well, we did get a 4-hour time window somehow at that point. That actually
The final exam.
yes. So
That was for the final.
Yes, I wanted to see if we can actually.
You haven't written the final yet.
Yes, but what I'm saying now is that actually a lot of people had problems at that time, and they also went, but they were able to get it done within the 4-time window. What I'm thinking is if we actually try that for the next couple of exams, it would definitely mitigate all of the problems that we would have in that time frame, and also give everybody enough time to finish.
I haven't decided yet on the times, but yeah, obviously, if there are problems in downloading things, then I'll have to extend the time.
Yes, so that would be great if we actually had it in that format. We're being tested on our knowledge, and this is definitely one of those things where timing.
All right, I've noted it. Any other questions?
Yeah, I have a question, but it's content related, like about the class.
Absolutely, go ahead.
So since we can prove that two languages are equal by reducing their DFAs to the same thing, can we prove that one language is a subset of another?
Yes, you can. You should be able to do that. Basically, we've already shown that we can do complementation, right?
Yeah.
And so if you have a language that is, if you want to show that R1 is a subset of R2, okay, R1 subset of R2, well, how about doing the following, R1 intersection R2? If that is R1, then R1 is a subset of R2, is it not?
So we can take the intersection of
You can
two.
take the intersection. We've already said that we can do complement for regular languages, therefore we can do intersection, and we can test whether this language, which is of course a regular language, is equal to that language, which is a regular language, and therefore that's the way to do it.
Okay, thank you.
Sure. Other questions? All right, so let's look at a finite automaton, a deterministic finite automaton within states. So D is A, Q, tau, Q sub 0, and F, and Q has n states. Now let's look at a word such that the length of W is equal to n. Now obviously if I take that word and start at the initial state, I'm going to get some state, P. Okay, and I'm not really interested in whether that state is accepting or rejecting. Now, W has n state, n letters, so W is A1, A2, AN, with the AIs being letters from the alphabet. And now I can define I start with Q0, then I have Q1, which is tau of Q0 and A1. And in general, Qi is tau of Qi minus 1 and AI. So the AI is going to get me to state Qi. And obviously Qn then is going to be tau of Qn minus 1 and An. So basically what this complicated way of writing things down is that I'm basically tracing through the automaton with that word W from the initial state to that state Qn, which is of course the P that I have here. Now, if we look at that, so how many states do I have written down here? How many states are these? Q0, Q1, Q2, Qi through Qn.
Is that n plus 1?
N plus 1 states. Now that's of course a bit of a problem because Q has n different states. So what does that mean?
Is not the reduced?
No. Has nothing to do with that. I have n plus 1 states in that list, Q0, Q1, Q2 through Qn. But Q, the set of states has only n different elements. So since I have here n plus 1 things written down, what do I have to conclude from that?
Go ahead.
I didn't hear what you were saying.
I think two of us were speaking, but I was just saying that means the transition function isn't going to cover this Q0.
No. I have here n plus 1 states.
I see.
We've already established that.
Okay.
But there are only n different states. So what does that mean?
One
There's a
state
mistake.
repeats.
Exactly. One of the states at least has to be repeated. So there exists I, say, less than j. They have to be different. So one of them is smaller, the other one is larger, such that qi is equal to qj for I between 0 and n. So what does that mean? Well, I start with Q0, and then I get to Qi. How do I get from Q0 to Qi?
Through tau.
Yes, but what do I have to do to Q0 in order to get to Qi?
Give the word input of the word of length n minus 1.
No, not n minus 1. I
No.
want to get to Qi.
The length of the word minus 1. That should be the input to the Q naught.
No, not at all. I want to get from Q0 to Qi.
Are we answering in the right direction? I think both me and the person that spoke both gave two separate versions, and they were both completely wrong. What would be the closer thing to look at?
There is only one correct answer, so there's nothing closer or further removed. How do I get from Q0 to Qi?
You apply a letter from the alphabet.
But which ones?
I suppose whatever is indicated in the transition function. So
No. You can tell me exactly which letters.
A
The
through
letters are under the alphabet. In the alphabet.
A through AI.
A what?
A through AI.
Not A.
Oh, not A. A1 through AI.
Yes. A1 all the way through AI. That gets from Q0 to Qi. Everybody clear? And now I go from Qi to Qj, but that happens to be the same. So how do I get from Qi to Qj?
use the epsilon, the empty.
No. There is no epsilon. There are no epsilon transitions. There's no epsilon. Forget about the epsilon.
Qi plus 1 to Qj.
But
Or Qi to Qj.
you're telling me the states. I want to know what letters get me from Qi to Qj.
I'm sorry. Then that would be AI plus 1 to AN.
No, not AN.
Well, we had it as AN. What would it be now?
No. I
AJ.
want to
AJ?
get to, yes.
AJ.
AI plus 1 through HA.
Thank you.
That gets me from Qi to Qj. Okay? And then I want to go to Qn. And that, of course, then how do I get from Qj to Qn?
Same as before, Qj plus 1. AJ plus 1 all the way to AN.
Correct. Okay, this is the same idea in all three cases. So the letters A1 through AI get me to QI. And then I have this loop which goes from Qi to Qj, except Qi is equal to Qj. So this is the same state. And that is AI plus 1 through Aj. And then finally from Qj to get to Qn, which is the P where I want to get, is Aj plus 1 through An. So what does that mean? It means that this word, W, can be written as V1, V2, V3. And the only thing I can unequivocally state is that V2 is how long? Well, because I is strictly less than J, I plus 1 through J is at least 1. Right, it's of length. So Vj is of length at least 1. V2 is at least of length 1. So this loop actually is going to use up at least one letter, because I is strictly less than J, so I plus 1 is less than or equal to J. And so that means that this AI plus 1 through Aj, these letters, there is at least one letter that describes this loop. It cannot be, of course, more than that, because we don't really have any idea what these I's and J's are, but we certainly can state that there is at least one letter involved to get from Qi to Qj. So V2 is at least of length 1. And now we can furthermore see that if we take Q0 and we do V1, and then we repeat V2 any number of times, S, and then we do V3, that this is always going to be P. Because if S is the repetition factor, then if S is 1, then we basically just do A1 through AI plus 1 through HA, HA plus 1 through AN, and that would be the word W. But if we take S is equal to 0, then basically we're getting rid of this AI plus 1 through HA. So we're getting rid of the V2. If I take S is equal to 0, then I have a word raised to the power of 0, which is, of course, epsilon. So basically, I make this V2 disappear by picking S equal to 0. And if I take S is equal to 2, then I go around twice. And if I take S is equal to 10, I go around 10 times. But I will always end up in Qj, and then applying that V3, which is AI plus 1 through AN, is still going to get me to the same state P. So this is for all S greater or equal to 0. So in this case, then V1 is going to be A1 through AI. V2 is going to be AI plus 1 through HA. And V3 is going to be HA plus 1 through AN. And that basically is this decomposition of W into 3 portions. The only thing that we can say is that of those 3 portions of these 3 words, the second one is of length at least 1. Can't say anything about the other 2. So if you find that puzzling, well, let's look at this automaton. 0, 1, 2, 3, so on, n minus 1, in, and then goes back. So let's just make this all A's. And this is the initial state, and let's just pretend that the alphabet is just A. So in this case, what do we have? We have basically, I'm sorry, this should be n minus 2, and this should be n minus 1. I want to have n states. Let's just make this final, but that's not really that important. So they're n states, and the word a to the n is going to get us from 0 all the way back to 0. So this is our word W. It is, of course, of length n. And now W is written V1, V2, V3. And what is V1 in this case?
Q0?
No.
A.
What is V1?
NAs.
No.
Would it be V2 minus 1?
No. Look.
I would want it.
All right. Let's ask a different question. What is the V2?
I thought we could make it what we want, and I would want to make it S
No, you can't.
Well, it's
absolutely not.
Oh.
This is given by that particular automaton.
Sure. We don't know what the front and the back are, and that the middle has to be multiples of 1, so I felt we could make the middle as big as we wanted, except including the start and the finish.
No. There is only one possibility for the V2. Because what is the loop? The loop is this, isn't it? If we go back to this loop here, in this case is, of course, this whole thing. That's the loop. If we take n A's and we look for the repetition, well, the repetition is the state 0, right? Nothing else is repeated when I do A to the n. From 0 to 1, 1 to 2, 2 to 3, n minus 2 to n minus 1, and n minus 1 to 0. So the state that is being repeated, this QI, is, of course, then 0, which immediately...
Does that mean, Professor?
Pardon?
Wait, does that mean that the repetition of n minus 1 and 0 are the same? Are they the same, I guess, are they equal to each other?
No. Why would the different states? N minus 1 is this state, 0 is this state.
But the repetition leads to it, right? So from n minus 1, they go to 0.
Yes. And so what state is repeated when I apply NAs?
The initial state.
The state 0, right? That's the only one that is repeated. 1 is not repeated, 2 is not repeated, 3 is not repeated, n minus 2 is not repeated, n minus 1 is not repeated. We're going from 0 to 1, 2, 3, etc., n minus 2, n minus 1, 0. So 0 is the one that is repeated, which means the V2 is what?
Zero?
How can it be 0? It's a bunch of A's. How many A's do you need in order to get to the repetition?
A to the 2n.
Why 2n?
Because you go through the list n times, the A's n times first, and then
And what? Stop right there. What if you apply n A's? Where do you, starting at 0, where do you get?
We end up at 0.
Correct. So what is V2?
NAs.
NAs. Okay. So what does that mean what V1 is? Remember, the statement is we can cut any word of length n into 3 subwords. Now, we've already established that the second word has to be a to the n. So what does that mean for V1?
A of n minus 1.
Oh. The whole word W is NAs.
So it's nothing.
Yes, but you have to tell me in
Epsilon.
Epsilon. Exactly.
Epsilon also.
And V3,
So V3
is also epsilon.
Yeah, 3, right.
Everybody clear?
Yeah.
All right, so that's what I'm saying. The only thing we can unequivocally state is that the second word must be at least of length 1, because we have to go around this loop, and that will consume at least 1 letter. We can't really say anything about this first A1 through AI. We can't say anything about this third word, AJ plus 1 through AN. But we can say something about the second word, AI plus 1 through HA.
Professor, you're muted.
Yes, I realized. Okay, so the second word, the V2, has to be at least of length 1. And that means now, in this particular case, this is of course a special case, but it is very clear that it is quite possible that both V1 and V3 are epsilon, and V2 is actually NAs. Generally, that's not quite true, but not always. But here is an example that clearly illustrates that you really can't say anything about V1. You really can't say anything about V3, but you can say something about V2. The V2 has to be at least of length 1. And in this case, it happens to be the whole word, and V1 and V3 are epsilon, but that's just because I cooked up this example so that it shows you what the problem in this case is. So that means that if I repeat this loop, which means if I repeat the word V2 as many times as I want, S times, 0, once, twice, 3 times, 10 times, I will get to exactly the same state, always, independent of what value of S I pick. If I don't go around at all, that would be S is equal to 0. So I do the V1, and then I do immediately the V3, and obviously I'm going to end up in Qn, which is the P. And if I go around once, then I have the actual word W. And if I go around twice, then obviously this is a longer word. How long is that word if I go around twice?
Beta the 2n.
Sorry?
So
the 2n.
You don't really know how long V2 is, but you can say if you go around a second time, then that resulting word, which is V1, V2, V2, V3, that is of course of length n plus length of V2, because this V1 plus 1 V2 plus 1 V3 plus V3 gives you n, and so adding another V2 is going to give you something of length V2 in addition. So this is obviously longer than the word W, which is of length n. And if I go around 3 times, I get an even longer word. And if I go around 10 times, I get progressively longer words. And so I have here an infinite set of words, all of which end up in the same state. Because it is going, that word, so I have basically V1, V2 to the power of s followed by V3. This is, for s greater or equal to 0, is an infinite set. Of words. Now, in general, of course, that doesn't necessarily mean this word is accepted, because we didn't really say anything about this P. So what can we do now if we have this situation where we have Q0 and then we have V1 to Q1 to Qi, and then this is equal to Qj, and there is V2, and then we have V3, which gets us to P. Now, if there is a word X that gets us to a final state, then obviously V1, V2 to the S, V3 followed by X is accepted for every S greater or equal to 0. So if I have a word that gets me from that P to a final state, then appending that to this set, or this language, will be a word that is accepted. So this is now an infinite set of words that are all accepted.
Professor?
Yes.
It just occurred to me, and I just want to make sure that this is what the right way of thinking about this. Whenever we just started right now, this whole process all went to now, we're actually looking at the word rather than the actual alphabet. So is all of these rules are like alphabet independent?
Well, they're not alphabet independent, because the word W is obviously over the alphabet A, but it has very little to do with the alphabet. It has exclusively to do with the word.
Okay, so this is just how the word is constructed, and from there on...
No, this is how the word behaves when you trace it through, when you trace the word through in the automaton.
Okay, so would this be like word parsing would be an example of this? This is basically
Yeah, you can think of it that way. But what is important here is that this implies a certain structure.
Okay, so every word will have this type of structure.
Every word that is long enough, every word that is of length n, that's how we started out, will be, you can cut it into 3 pieces such that the word W is the concatenation of the first word with the second word and that with the third word, and you can say that the second word is at least of length 1, and in the automaton, if you repeat the second word as many times or as few times as you want, then you will still end up with the same state. And basically what this then is this is known as the pumping lemma. For finite automata, for DFAs. Okay? And so basically what it says is if you have a word that is long enough, meaning the word is at least of length n, if the automaton has n states, the word is long enough, has n, is of length n, then it can always be decomposed into 3 words, v1, v2, v3, such that if you repeat the second word as many times or as few times as you want, you still end up in exactly the same state. And that then allows us to do certain things. For instance, we can show that there are certain languages that are not regular. So the claim is a to the n, b to the n greater or equal to 1 is not regular. Okay. So we want to show that. This is a simple language, bunch of A's followed by exactly the same number of B's. And we want to show that there cannot be a deterministic finite automaton that accepts this language. So not regular, that does not exist. A DFA for, call this L. Okay, so how do we prove that? Well, we assume the contrary. Assume there is a DFA accepting L. So that means we have D is equal to A, Q, tau, Q sub 0, and F. And let N be the number of states of D. And obviously L of D is assumed to be L. That's the assumption. We assume there is a DFA that accepts L. So the language accepted by that deterministic finite automaton is that given language, A to the N, B to the N. And, well, let me make this different. Let's call capital N the number of states of D. I don't want you to confuse that N with that N. Okay? So now consider A to the capital N, B to the capital N. Now that N, that capital N, is the number of states of that deterministic finite automaton that we claim is for that language L, accepts precisely that language L. So we consider A to the n, B to the n, and we cut off, we call W is A to the capital N. So call this Z, and obviously Z is W followed by B to the capital N. Okay, so that capital N now is this N, capital N, the number of states of that deterministic finite automaton that we assume accepts precisely that language. So, obviously, what we want to obtain is that this assumption is contradicted. And so the idea here is that because W is of length exactly capital N, that implies that W can be written as V1, V2, V3, and length of V2 is at least 1, and tau of Q0 W is equal to tau of Q0 V1 V2 to the S V3 for all S greater or equal to 0. And so now that holds for every S. And if I now append this B to the N to that, so I have tau of Q0 W, this is my W, and then I apply the remaining N B's, that of course is going to be a final state because A to the N, B to the N is in L, and therefore it has to be accepted by the deterministic finite automaton. And so now I'm going to look at this. This state is, of course, that state. And so I can do tau of Q sub 0, V1, V2 to the S, V3, and then I apply the NBs. This is, of course, exactly the same state. In particular, it is a final state for all S greater or equal to 0. And that, of course, immediately gives a contradiction, because if I take, say, S is equal to 0, then I have V1, V3, B to the N, which is A to the N minus the length of V2, followed by B to the N. This number is smaller than that number. So it cannot possibly be in the language L, because the language L consists only of words that have a number of A's followed by exactly the same number of B's. This word has fewer A's than B's, so it can't be in L, but it is accepted by the deterministic finite automaton, because it is going to end up in a final state for every S, so in particular for S is equal to 0, so that means this word is accepted by the deterministic finite automaton, but it obviously is not in the language. So what went wrong? Well, everything that we've done is straightforward. There are no assumptions. We picked that word, A to the N, B to the N. But the only thing we used from that was that the W is long enough. It is of length capital N, N being the number of states of the supposed deterministic finite automaton that accepts this language. And so by assumption, this word being long enough, it can be cut into 3 pieces, of which the second one has to be at least of length 1. And if I repeat that second one as many times as I want, S times, I still end up in exactly the same state. That's exactly what this here says. And that means, therefore, that A to the N minus length of V2, which is, if pick S is equal to 0, I get rid of this V to the V2. So I have only V1, V3. And since that is the number of little a's, this is n minus length of V2. And since V2 is of length at least 1, that is less than n. And then, of course, I have the nb's. So I have a bunch of a's, which is less than n, capital N, followed by capital NB's, which obviously is not in the language, because the language requires us to have the same number of A's as B's. But yet, it obviously is accepted by the deterministic finite automaton, because that gets us to a final state. So that is the contradiction. That shows that this assumption is wrong. Wrong, and so there does not exist a DFA for L.
Professor, what does regular mean in this context? Regular meaning that there is a DFA, or is regular something?
Regular is element of REG, which means you can find a regular expression, you can find a deterministic finite automaton, you can find a non-deterministic finite automaton. All of these are equivalent. We've showed that. And so in this case, of course, we're using the DFA. So if we can show that does not exist a DFA for that language, then of course we have also shown there can't be an NFA, there can't be a regular expression. Any of the other things that we've shown are equivalent. So if we can show that there does not exist a DFA for that language, we know that language is not regular.
What does a non-regular language do, or is there a reason why?
Here is one. This is not regular. We've just shown that.
Yes. So what does this do? Does it do anything in particular, or is it just not a useful? Do we have to watch out for not regular languages, or is it just another component that we might use later?
Well, what we're going to establish is we have regular languages, which is a certain set. And then there are context-free languages, which contain the regular languages. Strictly, there are context-free languages that aren't regular. And then there are other languages, and so ultimately, of course, there's the set of all languages. So this language, A to the N, B to the N, we've just shown is not in here. And we will then be able to show that this is in fact a context-free language. Context-free language is set of all languages. Say generated by context-free grammars. Let me quickly give you a little bit of a taste of what a context-free grammar is. You basically have variables and terminals. Variables are essentially variables, and terminals are the input symbols. So in this particular case, if we look at a to the n, b to the n greater or equal to 1, then the terminals in this case are a and b. That's basically our alphabet A in the automata, which in context-free grammars are going to be used. We're going to use the word T, the symbol T for terminals, and N for variables or non-terminals. The N's are basically variables, so the only other thing, the two other things that we need a starting symbol. Somewhere we have to start. And then we need productions. Productions basically allow you to take a variable and replace it by a string. The variable, say A, well, maybe call it B. Alpha. So we have terminals T, variables N, and alpha then is a string in N union T star. That allows us to replace a variable by a string. So in this particular case, let's say S is the starting symbol, and here is the production, A, S, B. That's a production that allows us to replace a variable S by ASB. And then we have another production, S goes to AB. So we can replace an S by either ASB or by AB. Now we start with S, and this double arrow is called a derivation. So we can, for instance, derive ASB. Or we could derive AB. So the trick is that we are ultimately only interested in strings that can be derived from the starting symbol using the productions, but only those strings that do not contain any variables. So we want to get rid of all the variables. So AB is a good string. ASB is not that good a string because it has a variable. But of course we could replace the S by AB, which would give us AABB. because we have the little a at the beginning, we have the little b at the end, and now the s could be replaced by a b using this production. Okay, so that gives me a b b. So I now have a b b, which is a good string because it doesn't contain any variables. Or I could have replaced the s by ASB, which will give me ASBB. I replace this S within the context of this leading A and the trailing B with ASB, the first production that I have here, which gives me AASBB. And now you can see that in this way, you can get rid of this S again using the second production, which gives you 3 A's followed by 3 B's, or you can replace it by the S by ASB, which gives you 3 A's followed by S followed by 3 B's, and then you can keep on going. And so what you can see then is, I hope, not very difficult to see, that ultimately what this grammar, which is a context-free grammar, fairly simple context-free grammar, generates is precisely a bunch of A's followed by exactly the same number of B's. So that means that we can generate A to the n, B to the n greater or equal to 1, using this grammar. So the grammar, let me write it down, context-free grammar, consists of, well, G is N, T, P, S. N is the alphabet of variables. N is also sometimes called non-terminals. I usually don't like to call things by something that they are not. That's kind of negativistic. So I use variables instead. T, of course, is terminals, the alphabet of terminals. P is a finite set of productions. And P basically is, well, if production is a variable to a string, A is in N and alpha is in N union T star. And finally, S is the starting symbol. And what we're then interested in is the language generated by the grammar, G, is the set of all W in T star, such that S, the starting symbol, derives in 0 or more derivation steps W. So this derives is, well, if we have alpha, A, beta, then that derives alpha, gamma, beta, if A goes to gamma is a production. So the alphas, betas, and gammas are basically strings over N union T star. So they consist of any number of terminals and variables, including epsilon, of course. And so we have a variable A produces gamma. So this is a production. And then if we have some stuff followed by the A, followed by some other stuff, then the A, the variable A, can then be replaced by the right-hand side of the production within the context of that leading and the trailing stuff. So the leading and the trailing stuff are not going to be changed, and the variable A is then replaced by the right-hand side of the corresponding production. So in the case of the grammar that I just gave you before, you have S is the full set of variables. You have A and B, these are the terminals. You have two grammar, through productions, S goes to A, S, B, or A, B, and so we're sort of keeping things simple. We take grammars, productions with the same left-hand side. So this is S goes to ASB and S goes to AB. Well, we're just grouping them together, and so we have S goes to either ASB or AB. So that simplifies things. We have to write less. And then we have the starting symbol S, and that would be the grammar for that language, A to the N, B to the N, N greater or equal to 1. So that then would show you a grammar, a context-free grammar, that generates that language that we have already shown is not regular, but it is obviously context-free because we've established that there is a context-free grammar that generates it. And so, as I said, the set of all context-free languages is the set of all languages generated by context-free grammars. And so that is then the set that is sitting here. We will have to verify at some point that the regular languages are actually a subset of the context-free languages. We don't have time for that. So that inclusion that this picture indicates still is not proven, but we will get to that.
Could we go to the slide 5, Professor?
Yep, here we go.
Okay, is it safe to say that a context-free language is actually, I mean, it's made out of regular expressions, and that's why we can't.
No. It's made out of words.
It's made out of words.
It has nothing to do with regular expressions.
So, but doesn't it mean that a word needs a what I would say a regular expression or a
No. It has nothing to do with regular expressions. I keep repeating that.
Okay.
You can. All right. Let me give you an example. Suppose I have this grammar. E goes to E plus E, E times E, open E closed, or ID. Well, that means you have a single variable, E. You have plus, times, open paren, close paren, and ID as terminals, and you have 1, 2, 3, 4 productions. Obviously, that single variable E is the starting symbol. Well, that allows you to generate all arithmetic expressions with plus and times. So if you have A plus B times C, A, B, and C, of course, being ID, instances of ID, we're not really going to go into detail. Then we have E goes to E plus E, and then we have that first E gives us A, the rest stays. Okay, then we have A plus, now we do the E times E. So this E is going to be replaced by that, E times E. And then we replace the first E by B. And then we replace this second, that E by C, A plus B times C. And so we have this arithmetic expression derived using this grammar. If you want to do A plus B parenthesis times C, then you do E goes to E times E, and then the first E can be replaced by open E closed E times E, of course, now. And then we replace the first E by E plus E times E. And now the first E is going to be replaced by A. Now that E is going to be replaced by B. And finally, the last E is going to be replaced by C. Oops, plus. And there it is. Now, this is obviously something that you can't, well, it's not obvious, but I'm telling you, you can't do with a finite automaton. Because just being able to do the parentheses, so you open paren, A, close paren, N times, obviously can be derived from E. And so there is no way, for instance, to do the matching of opening and closing parentheses, because obviously even if you didn't have that A, you need exactly, if you have a bunch of opening parentheses, you have to have exactly the same number of closing parentheses, and that is then very similar to this language, which we've already shown is not regular. So the language, if this is your grammar, then the language L of G is clearly not regular. But because we have this context-free grammar, it is obviously context-free.
In this situation, the grammar manipulates the words, or is the rules of the
No,
word.
the grammar allows you to generate a word. So you derive, for instance, A plus B times C. This is the derivation. Or you can derive open paren E plus B close paren times C. This is the derivation. Okay. Any other questions?
From the exam, I was gonna ask a question. The question about is the language countable? If it's not the intersect, but the inverted. I forgot the word we used. The complement. If the language is the complement of the other language, would that mean that it's not countable?
Yep.
Okay. Cool.
Obviously, if you have a set that is not countable and you take from that set away something that is countable, what is left is obviously still not countable. So if you take, for instance, the real numbers are not countable. If you take all the rational numbers away from the real numbers, the rational numbers are countable, but the real numbers minus the rational numbers are obviously not countable. And that's basically what this is very similar to. Okay, any other questions? All right, well then I will talk to you on Monday, the whatever it is, the 8th. All right.
Oh, Professor,
Yes.
I do have a question. Are we able to do any of the set with the information that you just gave us of set 2?
You obviously can do from exercise set 2. You should be able to do the first 2 questions, not number 3 and not number 4. We haven't gotten to that yet. But number 1, you should be able to do, and number 2, you should be able to do. Okay?
Thank you.
Any other questions?
Can I see slide 3?
Certainly. Look, I'm going to go, I'll show you all the slides. Okay, slide 1.
Okay.
Slide 2.
Okay.
Slide 3.
Thank you.
Slide 4. Slide 5.
Thank you.
And slide 6. I suppose when you wanted to see slide, 3, you wanted to take a picture, or do you have a question about it?
It was take pictures. Thank you.
Okay, yeah, that's what I thought. But if you have a question, by all means, shoot. Any other questions? All right, I will then talk to you on Monday. Bye-bye. Have a good evening.
You too, thank you.